Hello, everyone. Thank you for attending my session for the BIM Harambee conference, a month-long conference that brings experts from all over the world to present about their great experiences on BIM applications or digital applications in construction. I would focus on Africa. I am Henry Abanda. I am a reader in the School of the Built Environment at Oxford Brookes University in Oxford in the United Kingdom. A bit more about myself. Prior to being a reader, was a professor in Oxford Brookes University. I first of all obtained my bachelor's degree in maths and physics from the University of Buea, Cameroon. I later on obtained what we call a diplôme d'ingénieur in civil engineering from the École Nationale Supérieure Polytechnique Yaoundé, still in Cameroon. Then I went on to obtain a certificate in teaching in higher education in the UK in Oxford Brookes University, and then a PhD in construction informatics in the same institution. I'm also a visiting scholar at the École d'Ingénieurs d'État, which is a school in Institut National Polytechnique de Toulouse in France. These are floodings that recently happened in Senegal. And then we have a similar situation on the 21st of August, 2020 in Douala, the economic capital of Cameroon. Scenes like this are actually common today in many African countries and many parts of the world. At the time of this presentation, there is still wildfires raging over the city of California in the United States. It's been causing a lot of havoc. So there is an urgent need for us to be able to do something such that we don't have such occurrences due to climate change. And in order to do that, we have to examine the different sectors, how the different sectors of the economy affect our climate. And one that I'll be focusing on now or in this presentation is the buildings and construction, which account for more than 35% of global energy use and nearly 40% of energy-related carbon dioxide emissions. You can see that on those pie charts. And that is from the UN report, the Global Status Report 2017. Contributing 40% of energy-related emissions is quite significant, given that there are many other sectors of the economy. I would like to define embodied energy and embodied carbon and building information modeling, just for purposes of this presentation. Embodied energy / embodied carbon of a building is the energy expended in the extraction of the material or its material, and the energy with the transportation of the material to a construction site. Of course, in some publications, they will call that initial embodied energy, energy involved in the extraction of material from the source and transportation to site. Then they would separate it from what we call recurring energy, which is actually energy that is expended to maintain, replace a material, or even recycle a material or dispose of it after its useful life. But then in a nutshell, for now, let's accept that embodied energy and embodied carbon are energy and emissions associated with the extraction of raw material from its source to the construction site. Then I also define BIM. Of course, why am I defining BIM? Because this is an application of building information modeling in assessing the performance of buildings with respect to their embodied energy and embodied carbon. So BIM is defined as an innovative and collaborative way of working that is underpinned by digital technologies. That is the UK Construction Industry Council definition. And then another definition by Maud McDonald is a coordinated set of processes supported by technology that add value by creating, managing, and sharing the properties of an asset. From both definitions, BIM is actually a collaborative way of working that can be underpinned by technologies, not technologies as many have been saying, or that is common to hear a young or recent graduates calling BIM as a technology, or calling Revit to be a technology, which is just a tool that can aid in that collaborative way of working, or that can aid in managing the data that can be used in managing construction processes. Now, I'm talking about processes. What are the processes or processes of construction that issue from different type of applications? And these applications is what I would call BIM applications. Of course, I'm not going to focus on 1D, 2D, 3D. The D stands there for dimensions. 3D is, of course, our geometric model. 4D is project programs, so project scheduling. 5D is cost estimation, or 5D BIM. And then 6D is sustainability. 4D, 5D is a consensus in the industry as to what 4D is. 4D is definitely project scheduling. 5D is cost estimation. 6D, which is sustainability. In some books or in some publications, you find 6D to be facilities management, and in some you find 6D to be sustainability, or the other way around. So I'm just saying that there's no consensus from 6D onwards. It can be used, I've seen it being used differently in different textbooks or in different publications. But 4D, 5D, there is a consensus in the industry as to what they mean. Okay, and so our focus will be on sustainability, and specifically on embodied energy and embodied carbon, which I've defined them earlier. Now, we can pretty much calculate the embodied energy of every material in any type of building, starting from the Musgun there that you see on the left when I was still a young man exploring that building in Yaoundé, to a block of flats in Kenya, Nairobi, to the old presidency, the very first presidency of Cameroon, and then to a block of flats in London. But I'll be focusing on the block of flats, the one below, which is actually a project that I worked on some years ago in London. Now, why is it important for me to use BIM in order to compute or to assess or calculate the embodied energy of buildings? Now, as I've said, just as a reminder, embodied energy is energy used in extracting material from its source and transporting to site. Similarly, embodied carbon is the carbon that is used, or that is the carbon emission that is emitted, the carbon that is emitted when extracting material from source and being transported to site. So I will use carbon, but maybe in my calculations, you're going to see carbon dioxide. We definitely know the equations, the chemical equations between carbon and oxygen leading to carbon dioxide. So if I use carbon or carbon dioxide, we can actually compute one from another very easily from our knowledge of chemistry. Now, let's just look at the process of timber or wood being extracted from its source. The guy there is actually cutting a tree, starting from one, and then from there is loaded onto lorries, and then from the lorry maybe it's taken to a train station, and then from train station is transported by train to maybe to the seaport, where it is now loaded to ship, and then from the ship it can now be transported to Europe or America, and then drop into factories where it is now transformed to be used in buildings, or to be taken to sites and used in buildings. Now, if you think about just what takes place in that first source, at one, there is an engine saw that is being used in cutting a tree. That engine saw definitely depends on petrol. which is a form of energy, which actually is a form of energy. And the guy cutting the tree actually maybe is going to eat food and drink, which is actually some form of energy. And of course, so just thinking what takes place from stage 1 to stage 5, there is a complex supply chain. There's a lot of details going on there. And then also the sources, the food sources, or what is consumed in order to be able to execute these processes. And the fact that many different equipment are involved. So this is actually quite complex in order to be able to compute the embodied energy associated with a piece of wood that started as a tree, a piece of timber that started as a tree in Africa to ending up as a timber to be used in a building project in the UK, for example. But I'm going to simplify the calculation by using the formulae that are presented there, EEC's embodied energy of a given material K. Okay, K is a subscript equal to summation, the sum of 1 plus epsilon times the quantity K of that material times the intensity IK. Now that epsilon there is a waste factor. Okay, the same for embodied carbon, the waste factor there is lambda, and then the intensity there is tau. Okay, so going back to my building that I used, that I earlier showed you that I was going to use in my computation, the building in London, I've just zoomed the foundation there, and my calculation will focus on figure 1B, which is the pile, the concrete pile. Now, let's assume that the construction waste is 0. Then the simplified version of the formula will be embodied energy, which is quantity times intensity, embodied energy intensity, and the units are kilogram times megajoules per kilogram, such that the kilogram can cancel the kilogram, and then you are left with megajoules, which is dimensionally consistent. Okay, then we also have embodied carbon, which is actually the quantity times embodied carbon intensity, which is kilogram times kilogram carbon dioxide divided by kilogram. Again, the kilogram takes off, and then we're left with kilogram carbon dioxide. Then we also have cost, which is just to understand that formula, let's go back to cost. Cost is really given as quantity times unit cost. And the quantity there could be in kilogram, it could be linear measurements, it could be volumes, it could be meter square, times unit cost, which is pounds per kilogram, or pounds per meter square, or pounds per meters cube. And then if you cancel the kilograms, then you get a cost in pounds, or it could be in shillings, it could be in francs CFA. Then similarly, we have cost of concrete, which is like quantity times unit cost, which is like meter cube concrete times pounds per meter cube, and then you are left with pounds. So think about intensity to be something like that. Intensity to be energy intensity to be energy all over kilograms, or all over meters cube, all over any linear measurement or any unit, such that you multiply that intensity by the quantity that you've used, that you've chosen, and then you are left just with energy. Similarly for kilogram carbon dioxide. That means, for example, if you are told that if you use a kilogram, if you use 10 kilograms of steel in construction, and then the energy intensity of steel is, say, for example, 20 megajoules per kilogram, then to get the total embodied energy for the steel used in the project, you multiply that intensity by the original quantity, or by the quantity that you've actually computed. Similarly, for concrete, if you are told that the embodied energy intensity of concrete is 1 megajoules per meters cube, then, and you've used 10 meters cube of concrete, then you just multiply 10 meters cube by 1 megajoules per meters cube, and then the meters cube will cancel out, and you'll be left with 10 megajoules. Now, the question is, where do you find those intensities? Just like in my previous slide, we talk about cost. We have cost there, which is something like unit cost. You either get it from suppliers or you get it from professional databases or professional books. And in the case of the UK, we'll get it from what we call SPONS, which is widely used, or BCIS database. So for the embodied energy and embodied carbon intensity, we have a table that has been developed by the Bath University, usually called Bath Inventory of Carbon and Energy. And this is quite useful for estimating the embodied energy and carbon dioxide of buildings. And some countries have theirs as well. So for example, let's just look at aluminium, which is an element or a material, a common construction material. The general aluminium, we're 155 under the embodied energy intensity column, and then 8.24. That means if you use 1 kilogram of aluminium, you'll be expending 155 megajoules. Similarly, if you use 1 kilogram of general aluminium, you'll be emitting 8.24 kilogram carbon dioxide. Now, look at virgin aluminum, recycled aluminum below there. If you use 1 kilogram of virgin aluminum, you will be expending 218 megajoules. If you use recycled aluminum, 1 kilogram, you'll be expending 29.0 megajoules. Similarly, if you use 1 kilogram of virgin aluminum, you'll be emitting 11.46 kilogram carbon dioxide. If you use the recycled one, then you'll be emitting 1.69 kilogram carbon dioxide. That tells you that logically, you should be using recycled aluminum if you are to minimize emission to the atmosphere. Going back to the concrete pile, what do you need? What are the elements or the data that you need in order to be able to calculate embodied energy? First, you need a material inventory. You need to know the different elements or the different materials that have been used in your project. Then you need an emission inventory database. An example is a bath ice. And then you need the material density tables. The reason you need material density tables is because usually most of the time you're going to get your materials in volumes or meters cubed. And if you have the material in volumes, you can actually use density to get kilograms, partly because our bath inventory is only the units there are megajoules per kilogram or kilogram carbon dioxide per kilogram. So you need densities in this case. Now, to calculate the mass of the prefabricated pile, which is what I'd shown you previously, you would need the volume, because through volume and mass, through volume and density, you can get the mass. And the volume of that pile that I showed you previously is calculated as cross-sectional area times height, which is pi reduced square times height. And the height of that pile is 1.5. So if you substitute those values there, you get volume is 0.106 meters cubed. Now, in general, as we've said, the quantity of any material is given by its density times volume, which is here. And then given that we are dealing with prefabricated concrete pile, the density is 24 kilonewton per meter cube times 0.106 meters cube, and that gives us 254.4 kilograms of prefabricated concrete pile. Then the total embodied energy now, we now have to go to our bath ice and then read our embodied energy intensity. On doing that for concrete, it is 2 megajoules per kilogram. So multiply that by the quantity to get 508.8 megajoules. Similarly, we have to look for the corresponding embodied carbon, okay, which is 0.22 kilogram carbon dioxide per kilogram. Multiply by that total quantity, then you have it as 55.97 kilogram carbon dioxide. Now, if you do like that for all the materials, we may end up having a spreadsheet like this. And just imagine having to do that for every material in a building. How many components are there in a building? There are so many of them, so many different components in a building. So it is quite exhausting, tiring, and error-prone if we were to do it manually, as I've done. So that is where, and even when we do that, we have to be able to organize our data in a standard that we know compared to what we have here. This is what we usually get if we do it manually and not organized. But if we organize it, we should be having something like this, which is similar to our bill of quantities that we usually have, which is structured according to work breakdown structure. Okay, so if we have it like this, this is an organized way. We can determine the embodied energy for substructure, superstructure, services, and then, of course, we can now align it with the cost. And then if we have the cost by the side, we can make judgment that, oh, the substructure is emitting this amount of emissions, and then the cost is this, and we can make a sensible judgment whether we can change our material to have lower emissions and perhaps higher costs, or go for cheaper material and then higher emissions. It really depends. But then what I'm saying here is that we should be able to compare our emissions and the energy wasted in our construction materials with cost in a very, very structured and organized way. So I'm now going to show you a demo on how to do this using BIM, okay, instead of calculating as I've done in the previous slide. So I'm going to do that now using BIM. So to do that, I'm going to use this building, which is quite complex and usually comes with Revit. When you install Revit, one of the leading BIM designing tool. Then of course, you can actually access the embodied carbon or embodied energy database inventory developed by the Bath University through the link. That's a screenshot of the page. If you can pick this link here, you can actually access and download the full database from there. So we need quantities now, okay? We need quantities and then we need embodied energy intensities. How do we calculate the quantity from this building? Of course, we can do it manually, which we don't want to do. We've established that doing manually is error prone. And to do that, using Revit, we usually go to our view and then go to material takeoff. And then here, I'm just going to generate quantities from the whole building. So I'm going to call this one BIM Africa Demo 1, and then say OK. And then I'm going to cross some of these properties across. Material name, we want to know the material name, whether it is concrete, and then we want the volume. Just for now, let's leave these 3 properties. Now, also, let me go to formatting and show you something. If I go to volume there, I can actually change the unit, because you can see volume there means meter cube. I can actually go out here and say I don't want any units. But for now, let me leave units there and then generate quantities automatically. Okay, we can now see the quantities have been generated automatically. And you can see there's a certain concrete there. The quantity is 311.21 meters cube. Now I'm going to generate another one. I'm going to generate another quantities here for reasons I'm going to explain later. So we have material takeoff. Again, I'm going to say BIM Harambee Africa Demo 2. then okay. I'm going to look at family type, cross it over, material name. Where's material name? That's it there. And then material volume, whatever there. Then now, in my formatting, I'm going to go back to volume and then change formatting, changes. Then I'm going to say none for the units. Are you going to see the difference? Now, when you see the difference, when you look at this now, the difference is that you don't have units here. You understand why. I'm now going to export this and do my computation in an Excel spreadsheet. I'm going to do my computation in an Excel spreadsheet. So I'm going to go to File, File, Export, then go to Reports, choose Schedule. Once I choose Schedule, I'm using Demo 2 with no units. I'm going to go to the desktop and then choose the folder that I have this one in. This is a text file. Take note, that is a text file. I'm going to say, okay, okay. Now, I need to open Excel to be able to read that text file. And to do that, I will now have to switch and then go to this. Go to an Excel spreadsheet. Then browse this. Go to my desktop. Then change it here to text file to see the file I've actually exported. Then I'm going to say, okay, okay. So I have this, and you can see here at the top, that is actually BIM Harambee Africa Demo 2. Now we have our volume here, okay, which is in meter cube. The reason I have this without units is if I had brought units here, it would be difficult for me to multiply numbers. So I just decided to remove the units as I showed you earlier. So what I need now is to add another column for density. And then I put there kilogram per meter cube as my unit. Then I'm going to put embodied energy intensity. So I'm going to just put here IEE. Then, and we know, of course, that this one is megajoules per kilograms. Then I'm going to put here ICO2, and I'm going to put kilogram carbon dioxide divided by a kilogram. Or if I put the density there, I need to insert here mass or quantity Q in kilogram. Then I'm now going to put here embodied energy in megajoules, and then embodied carbon in kilogram carbon dioxide. Then I have my quantity here. So I'm going to look for the density of this, which is 24, concrete, 2400 kilogram per meter cube. And of course, the kilogram here now will be this volume times this. And then I can now pull it to calculate the quantity for all the different materials. So clearly, I'll struggle to multiply them. Now, I need to go back to my slide, and then I get the embodied energy intensity for concrete, for example. Now, let me go back again and share my PowerPoint. And then I move from here. That's a screenshot of bath ice. So the one that I'm interested in is concrete with compressive strength between 20 to 25 megapascal. The embodied energy intensity is 0.74, and then the embodied carbon dioxide is 0.1. So I'm going to go out of this again. I'm going to go back again. I apologize for the different shares. So I'm going to go back again and choose this. And then I'm going to enter the 0.74 and here 0.1. Then my embodied energy there will be quantities in kilograms times that, and then this will be my quantity there times that. Then I can now just pull it downward, below. I can do the same there. And then it calculates for me. If I enter all the values there, I'm just going to get this automatically. And I can actually put my cost column as well. I can actually put my cost column by the side and then compare my embodied energy and embodied carbon with the cost of the different elements. Okay, so that is how you use Excel and Revit with bath ice to be able to calculate the embodied energy and embodied carbon or carbon dioxide of buildings. I'm going now to go back to my PowerPoint presentation and continue till the end. So as some of the projects that we've done in the past that has to do with embodied energy and embodied carbon, some years ago, we developed a plugin for Google SketchUp at the time, which is now called Tremble SketchUp. And that plugin allows you to be able to simultaneously determine the cost, time, embodied energy, operational energy, embodied carbon, operational carbon, and waste of a project as you are designing it. So by the time you have 4 walls, a floor, and a roof, you should be able to look to see the cost, the time, the energy, carbon. I mean, when I talk about energy, it's embodied plus operational, and then carbon is embodied plus operational, and the waste on the dashboard, as you can see there. We've also done the same with Revit, where we develop a plugin that allows us to measure simultaneously the cost, the embodied energy, and carbon dioxide, and then get the results on the dashboard, and then align the results to standard measurement methods. In this case, new rules of measurement, which is quite commonly used in the UK. And some of our output have been published. You can actually get them. Those are journal papers that you can get from Science Direct. And then we have these two are open sources. You can actually just type those names and then you see, you find them on the internet. So we started off by looking at the major concerns that we have nowadays, which is floodings, hurricanes that results from climate change. And then we went on to establish that there is a need for different sectors to contribute to mitigating the impact of climate change that is already affecting us. And we focus on the construction, the buildings and construction sector, which actually represent a significant, or which actually emits a significant amount of emission of greenhouse gases to the atmosphere. And then we did our manual computation to illustrate how embodied energy could be calculated using calculating volumes of components manually, and then using the bath ice together with densities to density of the material to calculate the embodied energy and embodied carbon. We saw that it was quite challenging or time consuming if we want to think about a number of materials that we have in a building. Then we now came in with a proposition that we can actually use Revit, which is one of the BIM authoring tool, merge it with Excel, and then with the bath ice to calculate automatically, or at least semi-automatically, the embodied energy and embodied carbon of buildings. And the trick there lies in one, being able to generate quantities from Revit automatically. Two, being able to read correct values from BAF eyes. Of course, if you are in a country where they have a similar material inventory, then you can use that. But if you are not, I think it is an opportunity for you to start developing or sponsor research that can actually help you to have a database or an inventory database with the performance of all the material with respect to embodied energy and embodied carbon, so that the industry can actually use in evaluating the performance of their project. Thank you very much. Asante Sana. And if you have any questions, please email me at abanda@brooks.ac.uk. Thank you.